Good morning, dear students. We have been discussing about the different allotropes. Allotropes means they are having this similar chemical properties but different physical properties, isn't it? So far we have discussed the allotropes of carbon, isn't it? So right now we are going to discuss the allotropes of phosphorus. Okay, so phosphorus, it has got different allotropic forms. Say for example, white phosphorus, then red phosphorus, then black phosphorus, then scarlet phosphorus, then metallic or alpha black phosphorus, alpha black phosphorus, then beta black phosphorus, violet phosphorus, etc. So these are the different types of different allotropes of phosphorus. Okay, so we have to go through one by one, and also the most important forms or allotropes of phosphorus are white phosphorus, red phosphorus and black phosphorus, that you have to study in detail. White phosphorus, red phosphorus and black phosphorus. Okay, I will show you one photo of this white, red and black phosphorus. Okay, see, these are the three different allotropes: white phosphorus, then red phosphorus and black. See, this red phosphorus, it is almost ionic iron gray color. Okay, you know the color of iron. So this red phosphorus, it has got an ionic gray color, iron gray color. Okay, and this is black phosphorus, this is white phosphorus. Okay, so these are the three main important allotropes of phosphorus: white, red and black phosphorus. Okay, if you want to see more images, you can search Google. Okay, Google images, there you can see the different forms or the different images of these different types of phosphorus. Okay, different allotropes of phosphorus. So let us go through one by one, and the first one, that is the white phosphorus. White phosphorus. See, this white phosphorus, it is obtained by cooling the vapors of phosphorus. Obtained by cooling the vapors of phosphorus. Obtained by cooling the vapors of phosphorus, and also in the pure form it is translucent. Pure form it is translucent, white waxy solid. Translucent white waxy solid in the pure form. Okay, then white phosphorus, it is soluble in water, and insoluble in carbon disulfide. Insoluble in carbon disulfide. Soluble in water, insoluble in carbon disulfide. Also this white phosphorus, it is poisonous. White phosphorus is poisonous. And also at 800 degrees Celsius or below 800 degrees Celsius, this phosphorus, it corresponds to the formula P4. Okay, below 800 degrees Celsius, the formula will be P4, or it will be existing as P4. Okay, then above 800 degrees Celsius, it will be coming to, or it will be dissociating to P2. Okay, below 800 degree it is P4, it exists as P4, and above 800 degrees Celsius it exists as P2. Okay, and also at 1700 degrees Celsius also this will be existing as P2. Okay, so at these two temperatures, above 800 degree, that is at 1700, also it will be existing as P2. Then its melting point of this white phosphorus, melting point is 44.1 degrees Celsius, and the boiling point is 280 degrees Celsius. Then coming to the reactions, it will be dissolving in, it will be reacting with NaOH, that is it will be reacting with boiling sodium hydroxide solution and in an inert atmosphere. To give phosphine pH3. Okay, it will be dissolving in boiling sodium hydroxide solution in an inert atmosphere to give pH 3 phosphine. Okay, So let us write the reaction. P4 plus 3NaOH plus 3H2O plus giving pH3 phosphine plus 3NaH2PO2. 3NaH2PO2. This is sodium hypophosphite. Sodium hypophosphite. Okay. So this is the reaction with sodium hydroxide. It reacts with boiling sodium hydroxide in an inert atmosphere to give phosphine, pH3, that is phosphine. Okay. Then coming to the structure of this P4 molecule, it will be like this. P, then another P, P4. It just came to the rhombus form. Okay, this is P4 molecule. Just it will be like this. Okay. P4 molecule, P. Okay, so this bond angle, it is 60 degree. So this is the structure of phosphorus. See, what about the structure? What is the geometry of this particular P4 molecule? It is tetrahedral geometry, isn't it? It has got a tetrahedral structure and also 4 discrete molecules. That means 4 P4 atoms are there joined together, and these phosphorus atoms, they will be lying at the 4 corners of a regular tetrahedron. And also each phosphorus atom, it is linked to 2 other phosphorus atoms, isn't it? One phosphorus, not 2, it is linked to 3 other phosphorus atoms. While considering this phosphorus, it will be linked to 1, 2, 3. So this phosphorus, it is bonded to 3 other phosphorus atoms. Okay. And also all these bonds are covalent bonds. Okay. All the bonds present here are covalent bonds, and also it has got a tetrahedral geometry joined together by covalent bonds. Okay. So this is about the structure of P4 molecule. Then again, this P4 molecule, it readily catches fire in air. Okay, P4, it readily catches fire. That means it will be highly reactive with oxygen. P4 plus 5O2 giving P4O10. So highly reacts with, it is highly reactive with oxygen or easily catches fire in air, and also it forms dense white fumes of P4O10. P4O10, dense white fumes of P4O10. Okay. So this is about the white phosphorus. Okay. Then coming to the case of red phosphorus. Red phosphorus. Red phosphorus, it has got an iron gray luster or iron gray. It has got a little shiny appearance. Okay, iron gray luster, and also it has got no smell or no odor. So it is odorless. Then not poisonous. Not poisonous. Then insoluble in water. Insoluble in water. Then insoluble in water as well as carbon disulfide. Okay, insoluble in water and carbon disulfide. Then denser than white phosphorus. Denser than white phosphorus. Also less reactive than white phosphorus. Less reactive than white phosphorus. And also does not glow in dark. At the same time, the white phosphorus, they will glow in dark. Okay, does not glow in dark. So these are some of the physical properties of this red phosphorus. It has got an iron gray luster, odorless, non-poisonous, insoluble in water and carbon disulfide, denser than white phosphorus, less reactive than white phosphorus, and does not glow in dark. So these are some of the properties of this red phosphorus. Then coming to the preparation of this red phosphorus, it is obtained by heating white phosphorus. Preparation. Prepared by heating white phosphorus at a temperature of 250 degree Celsius. At a temperature of 250 degrees Celsius in a cast iron egg-shaped vessel. Cast iron egg-shaped vessel. In a cast iron egg-shaped vessel, it is heated. This white phosphorus is heated up to 250 degrees Celsius. And also there air is not used, there carbon dioxide is used. Carbon dioxide, so this reaction will be carried out in presence of carbon dioxide or coal gas. Carbon dioxide or coal gas. Then the white phosphorus, it will be converted to red phosphorus. So this is about the preparation of red phosphorus. It is prepared by heating white phosphorus at 250 degrees Celsius in a cast iron egg-shaped vessel in presence of carbon dioxide or coal gas. Okay, so this is about the preparation. Then while coming to the reactions of this red phosphorus or the chemical properties of red phosphorus, when red phosphorus it is heated, what happens is that this red phosphorus it will sublime and it will be converted to vapors, and this vapors means on condensing these vapors we will be getting white phosphorus. So we can convert white to red as well as red to white. Okay, red phosphorus when sublimed we will be obtaining vapors, and these vapors on condensing, on condensation we will be having white phosphorus. Hope you are clear. These vapors on condensation we will be having white phosphorus. Okay, so we can change white to red as well as red to white. And also coming to the structure of red phosphorus, it will be it will be a polymeric type of compound or structure. This red phosphorus has got a polymeric structure. That means it will be so many discrete units will be joined together to form this P4. Okay, so let us draw the structure. I am not good at drawing, okay, so you have to excuse me. Then this P, see this is a single, this is a discrete unit of P4, isn't it? And also it has got a tetrahedral geometry. Then again another phosphorus. Then again another P4 unit. So like this it goes on. Okay, so this is an extension of. So see all these units, these are single P4 units or discrete units, they are joined together. So just like polymeric units, this structure it will be having, and also it is having a tetrahedral geometry. So each P4 unit will be having a tetrahedral geometry. Tetrahedral geometry. Tetrahedral geometry. Okay, so this is about the structure of P4. Structure of P4. Okay, so this is about the case of red phosphorus. Then you have to go through alpha black phosphorus or metallic phosphorus. Alpha black phosphorus or metallic phosphorus. Alpha black phosphorus or metallic phosphorus. See here, alpha black phosphorus, it can be prepared from red phosphorus. So when red phosphorus, it is heated in a sealed tube. When red phosphorus, it is heated in a sealed tube. Delta means heat. Okay, it is heated in a sealed tube at a temperature of about 803 Kelvin. We will be having this alpha black phosphorus. We will be having alpha black phosphorus. So red phosphorus on heating in a sealed tube at 803 Kelvin, it will be converted to alpha black phosphorus. And also while coming to the reactions, it can be sublimed in air also. It can be sublimed in air. That means it will be it is reactive in air. And it will be having monoclinic or rhombohedral crystals. This alpha black phosphorus, it will be monoclinic crystal or rhombohedral crystal. I'm not showing all the pictures of all the images of this alpha black phosphorus or other allotropes. Shown only three two, because sometimes copyright issues may be involved since I am showing these videos in YouTube channel. Okay, so I am not giving you the pictures of this alpha black. If you want, you can search it in Google Images. Okay. So alpha black phosphorus, it will be having monoclinic or rhombohedral crystal, and also it is a very stable allotrope. It is a very stable allotrope, and also it does not conduct electricity. It does not conduct electricity. Does not conduct electricity. Okay, so this is about alpha black phosphorus. Then coming to the next allotrope, that is the beta black phosphorus. Beta black phosphorus. Here also this beta black phosphorus, it is prepared from white phosphorus. So white phosphorus, when heated to a temperature of 2000 degrees Celsius, imagine the temperature, it is 2000 degrees Celsius, and also at a very high pressure, and the pressure it is about 4000 atmosphere. Okay, so imagine the temperature and pressure, it is 2000 degrees Celsius and 4000 atmosphere, and also one more condition, in an inert atmosphere. In an inert atmosphere. Okay, so we will be getting this beta black phosphorus. Beta black phosphorus. Okay. Then one more method of preparation. This is one method. Then the second method of preparation, it can be prepared by heating white phosphorus at a temperature of 220 to 370 degrees Celsius for 8 days. Continuous heating for 8 days in the presence of mercury as a catalyst. So here mercury is used as a catalyst. So we will be having beta black phosphorus. Okay. So two methods of preparation. So these are the two different methods of preparation from white phosphorus. And then coming to the structure of this beta black phosphorus. Structure of beta black phosphorus, it will be like this. It is just a hexagonal layer like structure. This see, it has got a layer like structure. Similarly here P so this is the structure of phosphorus. It will be extending. Okay. So all the phosphorus atoms, it will be linked to 3 other phosphorus atoms. Okay. And also this beta black phosphorus, it has got a crystalline structure or crystalline nature. Crystalline nature. Then see, it has got a layer like structure, isn't it? It is present as layers. Layer like structure. Layer like structure, and also see, one phosphorus, it will be bonded to 3 other phosphorus atoms. 1, 2, 3, isn't it? While considering this phosphorus, 1, 2, 3. So one phosphorus atom, it is covalently bonded to 3 other phosphorus atom. One phosphorus atom, it is covalently bonded to 3 other phosphorus atoms. Okay, and also the bond angles, while considering the bond angles, this P bond angles, that means this particular bond angle P bond angles will be 90 degree. Next point, P bond angles will be 99 degree. And also the PP bond distance will be 218 picometer. pp bond distance. That is, this bond distance will be 218 picometer. Okay. Then these are flaky crystals. Flaky. The crystals will be flaky in nature, just like sodium hydroxide. Sodium hydroxide will be obtained as flakes. Okay, so just like that, this beta black phosphorus will be flaky crystals, and also it will be resembling the structure of graphite, isn't it? Graphite, we had written the structure. So the structure, it is almost similar to graphite. Structure of this beta black phosphorus, structure of beta black phosphorus resembles graphite. Resembles graphite. Okay. Then also it is highly polymeric. Highly polymeric because it is joined with other P4 atoms, isn't it? It is joined with, it is seen as layers, isn't it? So it will be seen as polymeric, or it is highly polymeric. Highly polymeric. It will be joined together to form polymers. And also it is good conductor of electricity. Good conductor of electricity. Good conductor of electricity. Okay. So this is about beta black phosphorus. I am not repeating. So next is the scarlet phosphorus. Next type is the scarlet phosphorus. Scarlet phosphorus. See, scarlet phosphorus, it is obtained by heating, preparation. First of all, preparation. It is obtained by heating phosphorus tribromide, PBr3. Phosphorus tribromide in presence of mercury. In presence of mercury at a temperature of 513 Kelvin. Phosphorus tribromide in presence of mercury at 513 Kelvin. We will be having pure scarlet phosphorus. That means 2P. Phosphorus, scarlet phosphorus P. This is scarlet phosphorus. 2P plus the byproduct is mercuric bromide, HgBr2. Okay, so this is one method of preparation of scarlet phosphorus. Then the second method of preparation, it can be prepared by heating amorphous scarlet powder. Amorphous scarlet powder with a 10% solution of solution of phosphorus in PBr3. So a mixture of these two, amorphous scarlet powder plus a 10% solution of phosphorus in PBr3. So this is a boiling solution, 10% boiling solution of phosphorus in PBr3 for about 10 hours. On boiling these two to 10 hours, okay, we will be having this scarlet phosphorus. And also it will be resembling red phosphorus in physical properties. Resembles red phosphorus in physical properties. Resembles red phosphorus in physical properties and resembles white phosphorus in chemical properties. Resembles white phosphorus in chemical properties. Okay. So this is about scarlet phosphorus. In your textbook, just the preparation is mentioned. Then the next is violet phosphorus. Violet phosphorus. See, violet phosphorus, first of all, we can go through the preparation. It is prepared by heating white phosphorus with sodium. Sodium means it will be in traces, okay, with traces of sodium at a temperature of 503 Kelvin under high pressure. White phosphorus plus traces of sodium at a temperature of 503 Kelvin at high pressure. Okay, so we will be getting violet phosphorus. This violet phosphorus, it is also crystalline in nature. It is also crystalline in nature. Okay, so these are the different allotropes of phosphorus that you have to study. Hope you are clear. So you have to study red, white and black phosphorus, and among that alpha black, then beta black, then scarlet phosphorus and violet phosphorus. Okay. Then the next one, coming to allotropes of sulfur. Allotropes of sulfur. Allotropes of sulfur. See, in the case of sulfur, you might have heard of rhombic sulfur, monoclinic sulfur, etc. Isn't it? So many allotropes are there for sulfur also. And the different allotropes of sulfur are, the first main one, that is the rhombic sulfur. Rhombic sulfur or alpha sulfur. Rhombic sulfur or alpha sulfur. Then the second one, that is the monoclinic. Monoclinic or prismatic or beta sulfur. Monoclinic or prismatic or beta sulfur. Then the third one, that is the gamma sulfur. Gamma sulfur. Then the fourth one, that is the delta sulfur or colloidal sulfur. Delta sulfur or colloidal sulfur. Then the fifth one, that is the plastic sulfur or gamma sulfur. Plastic sulfur or gamma. Here gamma is capital gamma. Okay. Gamma sulfur. Plastic sulfur or gamma sulfur. Then the sixth one, that is the angel's sulfur or epsilon sulfur. Angels means it is the discoverer. Okay. Angel sulfur or epsilon sulfur or cyclohexa sulfur. Angel sulfur or epsilon sulfur or cyclohexa sulfur. Then other allotropes are there which are cyclic in nature, and cyclic means it will be having S7 atoms, then S10, then S12, S18 and S20. So these are also different allotropes of sulfur. These are all cyclic sulfurs. Okay, S7, S10, S12, S18 and S20. They are all cyclic forms. So these are the different allotropes of sulfur: rhombic sulfur or alpha sulfur, monoclinic or prismatic or beta sulfur, then gamma sulfur, delta sulfur or colloidal sulfur, then plastic sulfur or gamma sulfur, this is capital gamma, then angel sulfur or epsilon sulfur or cyclohexa sulfur, then cyclic sulfurs S7, S10, S12, S18 and S20. Okay, then we can go through one by one. The first one, that is the rhombic sulfur or alpha sulfur. Rhombic sulfur or alpha sulfur. See, rhombic sulfur, it is the rhombic and monoclinic, it is the common forms of sulfur. And among this, rhombic sulfur, it is the most common one. And also, coming to the structure of this rhombic sulfur, it will be like this. The structure will be like this. First of all, I will be drawing the structure. Okay. These are the sulfur atoms. 1, 2, 3. 3 sulfur atoms. Then again, the next one, it will be just lying here. Then another one. You can join these dots, okay, just like a crown shape. Then you have to join these two. Okay, so these dots represents sulfur atoms. Okay, all these dots represents sulfur. Sulfur, sulfur, sulfur. So this is the structure of sulfur. How many sulfur atoms are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 sulfur atoms are there. That means this is S8 molecule. So these are discrete S8 units. Okay. And also coming to some of the properties of this sulfur. They are large yellow crystals. Large yellow crystals. I will be showing you the picture of this rhombic and monoclinic sulfur. Okay. See, this is rhombic sulfur and this is monoclinic sulfur. See, rhombic sulfur, it is large yellow like crystal, isn't it? Yellow crystal. But in the case of monoclinic, it is almost needle shaped, isn't it? They are needle shaped crystals, monoclinic sulfur, while rhombic sulfur, it is large crystal form. Okay. Rhombic and monoclinic. Okay. Then large yellow crystals, and also they will be these rhombic sulfur, they will be occurring in volcanic areas. Okay. And also they are prepared by evaporating. They are prepared by evaporating a solution of rolled sulfur in carbon disulfide. Prepared by evaporating a solution of rolled sulfur in presence of carbon disulfide. And also its melting point, it is about 385.8 Kelvin. 385.8. Then insoluble in water. Insoluble in water. Then soluble to some extent in benzene. Soluble to some extent in benzene, alcohol and ether. In benzene, alcohol and ether. Then it is readily soluble in CS2, carbon disulfide. Readily soluble in carbon disulfide. Okay. And also coming to the structure, it will be having a crown conformation. Okay, crown structure, it is just in the form of a crown. I don't know whether you will be seeing it as a crown. You can just refer your textbook. It is just like a crown shape structure. I am not good at drawing. Okay, so it has got a crystal structure with puckered S8 rings. Puckered S8 rings. And also a crown conformation. With a crown conformation. Okay, so this is about rhombic sulfur or alpha sulfur. Then the next one, that is the monoclinic or prismatic or beta sulfur. Monoclinic or prismatic or beta sulfur. See, this monoclinic sulfur, it is prepared by or it is obtained by melting rhombic sulfur. So we can convert all these allotropes into each other. Okay, so rhombic sulfur on melting, and then after that it is cooled. So first it is rhombic sulfur, it is to be melted and then cooled. Then a crust will be formed. Crust means a solid mass, and this solid mass, when a crust will be formed on cooling. Okay, so in this crust, two holes are to be made. Okay, and the liquid sulfur lying below the crust, which is not solidified, it is poured out through the holes. And also on removing the crust, colorless needle shaped crystals of beta sulfur, it is obtained. So first of all, rhombic sulfur, it is melted and cooled. Then on cooling, it becomes a crust like form on the surface. And while we are putting a hole on the two holes on the crust, what happens is that the liquid sulfur will be lying underneath this crust. Okay, and that it is not solidified, and through these holes, this liquid sulfur can be poured out. And on removing the crust, we can see colorless needle-shaped crystals of beta sulfur. And this beta sulfur, it will be stable at 368.6 Kelvin. Okay, stable at 368.6 Kelvin, and below this temperature, it will be converting to beta and below this temperature it will be converting to alpha sulfur. Alpha sulfur means rhombic sulfur. Okay, so below 368.8 it will be converting to alpha sulfur, and above 368.6 it will be converting to beta sulfur. Okay. It will be converting to beta sulfur. That means there is a transition stage at this particular temperature, isn't it? So at this particular temperature, above this particular temperature, it will be converting to beta sulfur, and below this 368.6, it is converting to alpha sulfur. So we can say that this temperature, that is 368.6 Kelvin, it is the transition temperature for this alpha sulfur as well as beta sulfur. Okay, this 368.6, it is the transition temperature. Okay, that means below this temperature it is alpha sulfur, and above this temperature it is beta sulfur. And also coming to the melting point of this particular allotrope, melting point it is about 393 Kelvin. And also soluble in carbon disulfide. Soluble in carbon disulfide. Here also it is it will be occurring as crystal structure. It will be in the crystal form. Here also it will be having cyclic S8 rings. It will be having cyclic S8 rings. So these are some of the points regarding this monoclinic or prismatic or beta sulfur. Okay, so you have to note down this transition temperature also. Then the next is the third one, that is the gamma sulfur. Gamma sulfur. Gamma sulfur or gamma monoclinic sulfur. This gamma sulfur, it is obtained by decomposing ethylene sandate of copper 1. Ethylene sandate, the structure you doesn't need to study. Ethylene sandate. So this ethylene sandate, it is a salt of copper 1, cuprous. Okay, ethylene sandate of copper 1 in presence of pyridine. Ethylene sandate of copper 1 in presence of pyridine. So when both these are mixed together and when decomposed, on decomposition, we will be having this gamma sulfur. Okay, we will be having gamma sulfur, and also this gamma sulfur, it will be existing as pale yellow needles. It will be existing as pale yellow needles. Here also this gamma sulfur has got a crystal structure, crystalline nature with cyclic S8 rings. Crystalline nature with cyclic S8 rings. Okay. So this is about gamma sulfur. Then the next one, that is the delta sulfur or colloidal sulfur. The fourth one, that is the delta sulfur or colloidal sulfur. First one, method of preparation. See here, this colloidal sulfur, it is prepared by passing H2S through nitric acid, concentrated nitric acid or KMnO4. See, nitric acid, it is a very good oxidizing agent, isn't it? So HNO3 plus H2S, on passing H2S over HNO3, we will be having this colloidal sulfur. This is colloidal sulfur. Plus 2 molecules of NO2 plus 2 molecules of H2O. Okay. Then one more method of preparation. This is the first method. Then the second method of preparation by passing H2S through water containing dissolved sulfur dioxide. Passing H2S over water containing dissolved sulfur dioxide, SO2 molecules. Okay. So the product will be, this is colloidal sulfur 3S, colloidal sulfur plus 2 molecules of water. So 2 methods of preparation for delta sulfur or colloidal sulfur. Okay. Then the next one, the fifth one, that is the plastic sulfur or gamma sulfur, capital gamma. Plastic sulfur or gamma sulfur. This plastic sulfur, it is obtained from the molten sulfur. Okay. When molten sulfur, it is heated to 350 degrees Celsius. When molten sulfur, it is heated to 350 degrees Celsius and then it is poured into cold water. After heating it to 350 degrees Celsius and then pouring into cold water, this plastic sulfur or gamma sulfur, it is obtained. We will be having plastic sulfur. Okay. So gradually, if it is kept as such, it will be hardened and then gradually it will be changing to rhombic sulfur. Okay. So after hardening, what happens? It will be converting to rhombic sulfur or alpha sulfur. It will be converting to rhombic sulfur. Okay. Then coming to the properties of this plastic sulfur. Plastic sulfur, it has got a dark color. It has got a dark color. Then soluble in carbon disulfide. Soluble in carbon disulfide. Then it has got cyclic S8 rings. Just as in the previous cases, it has got cyclic S8 rings and also long helical chains as well. Okay, a mixture of these two will be the case of this plastic sulfur. Long helical chains also. Long helical chains of sulfur atoms. Okay. Then one more point is that it can be converted into fibers. See, in Google Images you can see so many nice pictures of this plastic sulfur. It is converted to fibers. Okay. And then it can be converted to fibers, and this fibers, how we can obtain is that by heating this in an atmosphere of nitrogen at 300 degrees Celsius and then quenching in water. Heating to a temperature of 300 degrees Celsius in presence of nitrogen, that means inert atmosphere. In presence of nitrogen means in an inert atmosphere for a few minutes, and then quenching in water, we will be having this fibers. Okay. And these fibers, they can be stretched also. So, and also this plastic sulfur, it is considered as a supercooled liquid. Supercooled liquid. So these are some of the properties of this plastic sulfur. Dark in color, soluble in CS2. Then it is allotrope. This allotrope, it is a mixture of cyclic S8 rings and long helical chains. It can be converted to fibers. That means it should be heated to 300 degrees Celsius in presence of nitrogen and then suddenly quenched into water. Then we will be having this fibers. Okay. And also it is considered as a supercooled liquid. Then the last allotrope of sulfur, that is the angel sulfur or epsilon sulfur. Angel's sulfur or epsilon sulfur or cyclohexa sulfur. Cyclohexa sulfur. First of all, the preparation of this angel sulfur. It's prepared by pouring sodium thiosulfate Na2S2O3 into concentrated HCl. by pouring sodium thiosulfate into concentrated HCl and extracting the sulfur from toluene. Okay, so we will be having this angel sulfur, and this sulfur it is extracted with the help of toluene. Okay, extracting from toluene. So this is one method of preparation, by pouring sodium thiosulfate into concentrated HCl and then the sulfur it is extracted from toluene. And also one more method of preparation, the second one, that is in presence of H2S4 plus S2Cl2 giving S6 plus 2 HCl. This is another method of preparation, H2S4 plus S2Cl2 giving S6 plus 2 HCl. Then coming to the properties of this angel sulfur, first of all you have to draw the structure. It is almost like a chair form. Okay. Here one sulfur atom, 1, 2, 3, then 4, 5, 6. Okay, so how many sulfur atoms are there? This is 6 sulfur atoms are there. So this is in the S6 form. Okay, just like a chair form. You have been studied the stereochemistry, chair form and board form, isn't it? So it is almost similar to a chair form. And also all these are sulfur atoms. Okay, and also coming to the properties, it has got closely packed S6 rings. Closely packed S6 rings. Then highly reactive. Highly reactive means highly unstable, isn't it? Highly reactive and highly unstable. This S6 form is highly reactive and highly unstable. So this is about angel sulfur. You have to note down the structure as well. Okay. Then the last one, that is the different cyclic forms of this sulfur. The seventh one. Sulfur allotropes having S7, then S10, S12, S18, S20. Okay, so these allotropes, they are obtained by treating sulfur chlorides with hydrogen polysulfides. Okay, the general method of preparation. General method of preparation by treating sulfur chlorides with hydrogen polysulfides. Okay, so you have to write down some of the reactions given in your textbook. S2Cl2, this is sulfur chloride, plus hydrogen polysulfide, this is H2S8. Okay, giving S10 plus 2 HCl. So here we will be having S10 rings. Okay, then another one, S4Cl2 plus H2S8. Another hydrogen polysulfide reacts with sulfur chloride to give S12 plus 2 HCl. Okay, so this is another allotrope of sulfur. So these are cyclic sulfides. Okay, cyclic sulfurs, and also that means they are in the ring form, isn't it? And also they are unstable also. And this is paramagnetic also. Paramagnetic means it will be having unpaired electrons. So these allotropes, they are paramagnetic. That means they will be having unpaired electrons. Okay. So these are These are the different allotropes of sulfur. There are almost 7 types are there. So you have to study all these categories: rhombic, monoclinic, gamma, delta, then plastic sulfur, angel sulfur, then the cyclic sulfurs. Okay. So up to this, we have completed this allotropes of the different elements. That means we have seen allotropes of carbon, then allotropes of phosphorus, then allotropes of sulfur. Then in our next video, we can go through some of the applications of lithium, cesium, selenium and barium. Okay, some of the applications of the group 1 and group 2 elements or the representative elements. Okay, thank you.